Now let's take a look at theorem 4.10 on page 225. This theorem says that if you have, let me illustrate the theorem this way. Let's say your basis has 8 vectors, okay? If your basis has 8 vectors, then if you take any 9 vectors or 10 vectors or 11 vectors in V, those vectors need to be linearly dependent. So if you have more vectors than the number of vectors you have in the basis, then those vectors that you pick need to be linearly dependent. Okay. The way to prove that is quite simple, but it's tedious. The idea is simple, but it's tedious to write the proof. But let's see if I can do that here. The way to do that is that, okay, let's take m vectors. M vectors meaning that I'm picking more than what I have, more than the number of vectors that I have in the basis. So I pick m vectors with m greater than n, so I have more than n vectors. Now, I want to show that these vectors are linearly dependent. Now, these vectors here, they're not necessarily any of these here, okay? I just pick any m vectors. So the way to show that they're linearly dependent is to set this equation. I set the linear combination equals to the 0 vector. Now I need to see if these coefficients are not the trivial. If I solve this for the coefficients, the solution is not the trivial solution. Because if it turns out that these coefficients k1, k2, km are all 0, then they would be linearly independent. But it turns out we're going to find that out that they're the solution is not trivial. I can find some of those k not to be 0, so therefore they will be linearly dependent. Okay, so a way to do that is to take each of those vectors u and write each vector as a linear combination of the vectors in the basis. Because S is a basis, so each vector can be represented as a linear combination of the vectors in the basis. So this is what I do. Okay, I'll explain the red notes in a minute. So here's a linear combination. I set them equals to 0. Now I take each u and I write them as a linear combination of those v's. Okay, why do I use C11, C21? It's just to keep track of the coefficients because there will be a lot of them. See, for each, let's say for example I have n equals to 8 and m equals to 10, okay? So that means I have 10 vectors, and each of those 10 vectors I need to write as a linear combination of those 8 vectors. So you can imagine how many coefficients I'm going to have, how many scalars I'm going to have. I'm going to have 80 scalars, right? And a way to keep track of those scalars is to use 2 indices when you write the coefficients. So, for example, when I pick u1, and u1 is written as a linear combination of those v's, then I can write c11 and c21. So the first index here corresponds to the first scalar in the combination, and the second index corresponds to vector u1. This is the first vector u here. Like u2 here, so it's the first coefficient, second coefficient, and so on. But the second index corresponds to the u2. It's just a way to keep track, okay? It's just a notation. So in other words, I will have m times n coefficients to keep track, okay? So we'll put all those together. So each expression, I take each expression here and I squeeze them in here, okay? Substitute u1 with this expression, and then substitute u2 with this expression, and so on. So I'm going to have a huge sum, and that sum is equal to 0. So let's see what happens if I squeeze this in here. If I squeeze this in here, then k1 will multiply this whole thing here, the whole expression for u1. So it will be k1 times this term, k1 times this second term. And then if I look at the second expression, if I put that expression in here, k2 will be multiplied by this whole thing, and so on. Okay, now that we understand that it's going to be a huge expression, I'm going to try to collect all the coefficients for v1, and then collect all the coefficients for v2, collect all the coefficients for v3, and so on. So let's see what would be the coefficients for v1. So for coefficients for v1 would be k1 and then c11. That will be one from here. And then another coefficient for v1 would be K2 times C12. So this is actually K2 here. C12. Another coefficient would be K3, C13, and so on, until I reach the last coefficient for V1, which is Km, C1m. These are all the coefficients for V1. Okay, and then I need to collect all the coefficients for V2. It will be K1, C21, and then K2, C22, right? And then K3, C23, keep going, and then until I reach the last coefficient for V2, which is Km, C2m. And so that takes long. So I collect all the coefficients until I reach the last vector in the basis, Vn. Okay. So the coefficients for Vn would be what? K1 again times Cn1 and K2 times Cn2. Finally, Km times Cnm. That's the all those coefficients for Vn. And then remember, this whole thing is set to be equal to the zero vector. Okay. Now, look at this now. This is a linear combination of the vectors and the bases, right? Remember, if I go back here, these are the vectors and the bases. So I have a linear combination of vectors on the basis, and that's equal to the zero vector. Because the basis is linearly independent, all those coefficients must be zero. Not each coefficient, but this big coefficient here needs to be, this one here will be 0. This one here will be 0. Until I reach the last coefficient of Vn, this will be 0. All those n coefficients will be 0. That's why you see a big system of equations on page 226, because each of these coefficients is 0. So K1, C11 plus K2, C12 all the way to Km, C1m equals to 0. Right, and then K2, C21 plus K2, C22, and then Km, C2m equals to 0 until I reach the last coefficient, K1, Cn1 plus K2, Cn2, Km, Cnm equals to 0. Okay, that's a big system of equations. Notice that we are solving for the K1, K2, and Km, right? Remember, we're trying to find these coefficients here, K1, K2, all the way to Km, and see if they're 0. Well, one thing that you're supposed to remember from the first linear algebra course that you took, it says that if you have m variables, but you have fewer equations, then the solution is not trivial, okay? So for example, let's say, again, if m is 10, let's say number of vectors in the basis, let's say n is 8 and m is 10, so we have more vectors. That means n is 8, m is 10. So this means that you have 10 variables. You only have n equations. See here, C1, C2, Cn. So there's only 8 equations with 10 variables. So the conclusion is that we have more equations than variables in this linear system. Okay, therefore solution is not trivial. So in other words, sum of those k, sum of the ki's okay, may be non-zero. Therefore, these vectors here are linearly dependent.